All right, here we're going to look at continuous probability models. So continuous models are different from discrete models because we can have, any value between two given points, or there might be multiple intervals where that's true. So discrete models were like flipping a coin or rolling a die, right? We could only roll a 1 or a 2 or a 3 or a 4 or 5 or a 6. So we had a finite number of possible outcomes. We also could not roll like a 1.3 or something like that that's in between 1 and 2. So we're going to look at continuous models where we can do that. But we're going to start with the idea of a density curve. So a density curve just has two pretty simple properties. It's always on or above the horizontal axis. A lot of times we call this the x-axis if we're thinking algebraically. And it has an area of exactly 1 underneath it. So those are the only things we need. So for the first example, draw the density curve that corresponds to selecting a random real number x that's between 0 and 4. And so this is the real number portion of this, is where we're talking about, okay, it's not just 0, 1, 2, 3, and 4. So we certainly can pick out the number 1.3. We certainly can pick out the number 2.72931. We could pick out the number pi, right? So we would have anything in there between 0 and 4. So we're going to start with the horizontal axis, and this is going to be our random number x. So x can be anywhere between 0 and 4. And actually, I'm just going to move my 0 over, just a tiny bit. So let's put 0 here, because we're also going to need a vertical axis. And the idea is, everything between 0 and 4 is equally likely to come up. So we get what's called a uniform distribution. So all values are equally likely. And so that probability is going to be over here. All right, we're going to think about this like a probability very soon, right? And so we're going to say, well, okay, 0 through 4 is that's my interval of possible answers. Well, certainly my line is above the horizontal axis between 0 and 4, so that's good. The rest of the time it would just be 0, right? We can't get that. The second part is having an area of exactly 1. Well, the nice thing is this is a rectangle. And so our area is just length times width. And we know that the length here from 0 to 4, well, that's just 4. So the length is 4. We don't know the height. That's what we're trying to find, or in this case, I'm calling it the width. Same deal. And we know that the area, we were already told, is 1. So we can say 1 equals 4 times the width. And then we can solve for w, right? Just divide both sides by 4. And we end up getting that the width is 1/4. And so that's going to tell us the height here. So this is going to relate to probabilities. It doesn't mean that every number on here has a likelihood of 1/4 of being chosen. So we'll kind of get into, well, what does that look like? If we really think about it, the likelihood of any single number being chosen is 0, because there are infinitely many numbers between 0 and 4. So kind of an interesting little thing. Okay, so then let's take a look at continuous probability models. So a continuous probability model is some sort of probability model, right? We've seen this with discrete models before, so now we're looking continuous, but it's a probability model that assigns probabilities as areas under a density curve. So we're going to pull in our curve from up here and incorporate that for our second example. So we're going to say, use the density curve from the previous example to find the probability that a randomly generated real number between 0 and 4, which we're calling x, is, first of all, between 2 and 3, and then between 1.5 and 3. So what I did here and here was convert these into probability notation. So this just says the probability that x is greater than or equal to 2, less than or equal to 3. So basically x is between 2 and 3. So I just took this sentence and turned it into a probability statement. That's really all I was doing there. Okay, so let's take a look. We had our density curve, and we said the height here was 1/4, and this went from 0 to 4. And so if we're looking between 2 and 3, well, okay, let's toss in our other values here, 2 and 3. Then if we're saying, okay, this is the area under the curve, so let's look between 2 and 3, shade in that area, and we're basically saying, okay, what is this? So the area, again, is just going to be length times width or base times height, however you want to say that. But our base, or what we called length in the previous one, is just from 2 to 3. So that's just 1. And then our height, or our width, as we called it before, is 1/4. So there's a 1/4 or 25% chance that we land between 2 and 3 if we just randomly generate a number between 0 and 4. In part B, this one's pretty similar. The only difference in this case is we're going to back up to 1.5. You'll see that that doesn't really change a whole lot. So I'll put in my regular values, my integer values here. But of course we know 1.5 is just going to be halfway. I'll remind us the height is 1/4. So okay, 1.5, yeah, that's just halfway between 1 and 2. 3, kind of like what we did before. So we're looking at the area of this shaded region. So now the length, or the base, is from 1.5 to 3. So that's going to be 1.5. And the height, or the width as we were calling it, is 1/4. Right, of course you could use your calculator to figure this out, but we end up getting, depending on how you do this, 0.375. You could also convert this, right? 1.5 is 3 over 2 as a fraction, so this could be 3/8. Doesn't really matter. The idea is, that we get one of these answers. A lot of times seeing it as a decimal helps because then we can think of it in terms of a percentage. So there's a 37.5% chance that we randomly choose a number and it ends up between 1.5 and 3. Okay, our next example on this topic, this one's going to look very similar to a homework question. So books on reserve at a university library can be checked out for at most 2 hours. Pretty stringent, but that's the case with a lot of textbooks or something like that. The density curve for the amount of time the book is actually checked out is the shaded triangle shown below. So again, the max is going to be 2 hours, so we've got to stop there. The min, of course, is going to be 0 hours, and we see that certainly it seems like more people are holding on to the book for 1 to 2 hours than they are for 0 to 1 hours. Right, that's kind of what this density curve is telling us. The higher the value here, right, the higher up it is, that means the more people who are hanging on to it. So what is the probability that the book is checked out for less than 30 minutes? Well, okay, keep in mind that this scale is in hours. So of course we don't see 30 on there, but we could say 30 minutes, no problem. That's half an hour. So we just go, all right, half an hour is about here. And we can say, well, if I'm looking at less than 30 minutes, the shaded region I'm interested in is right here. All right, well, we want the area of that little triangle. So an area of a triangle is 1/2 the base times the height. 1/2 times something times something. So we're going to figure out what those somethings are. Well, the base isn't too bad because we're starting at 0 and we're stopping at 1/2, half an hour. So, okay, the base is 1/2. The height, however, this little piece right here, we're going to have to, be a little bit clever in how we figure this out. So we can use a bit of a pattern, right? We see that this is basically one big triangle, or we can think about it like, oh, this is a little linear function. That's kind of cool. Cool if linear functions are cool, I guess. So let's start with 1 hour, right? What would the value be on the vertical axis at 1 hour? Well, it looks like this is going from 0, 0 up to the point 2, 1. So it's probably going to be halfway in between on the vertical because it's halfway on the horizontal, right? And we're starting from 0, which is nice. So, all right, this looks like it's going to be the point, right? Half of the horizontal, so half of 2 is 1, and half of 1 is 1/2. So probably 1/2. We can kind of eyeball it. It looks like, yeah, it would be roughly 1/2, right? I just drew this in, so it's not perfect, but it's pretty close. And then we can say, okay, well, now I want to go half of that distance. So I'm going to here, and my, what we normally think of as my x value, but now it's my t value, is 1/2. So we cut this in half. And then we want to cut the vertical value in half as well. Well, half of half is 1/4. And that's going to be our height. So our height is 1/4. Also, if you're very algebraically inclined, you could figure out what this line actually is, or you could think about it in terms of slope. There's a lot of ways to do that. Okay, so we multiply this together, multiply all the numerators, I get 1. Multiply all the denominators, I get 16. Again, from here, you can turn this into a decimal if you need to, but for now, I'll just leave it as a fraction. I'm not worried about that extra little piece. Okay, then what's the probability that the book is checked out for more than 30 minutes? So that's going to be basically the rest of this area that we're interested in, right? All of this stuff. Well, remember, the area, the total area, is 1. And that was one of our basic properties for density curves. Total area is 1. Well, we already know what the little blue shaded region is. That's 1/16. So I guess the probability that t, right, the time that it's checked out, is greater than, again, we're measuring this in hours, so we can say greater than 1/2 of an hour, or greater than 30 minutes, is going to be 1 minus what is already accounted for by this little blue triangle. So 1 minus 1/16, otherwise known as 15/16. Again, you can calculate that. I'm not too worried about it, but the idea is getting the setup right. And that's kind of our general idea.